Remember in my previous video, I told you about the convolution theorem. The convolution theorem, the importance of the convolution theorem is it allows us to take the Laplace inverse of a function that is complicated and that cannot be broken down using partial fractions. So this function here is impossible for us to break it down using partial fractions. And now if we want to take the Laplace inverse of such a function, we will have to rely on the convolution theorem. So this is what I said in my previous video. I am going to write the definition of the convolution, and then we use that to solve the Laplace inverse of this function, which cannot be broken down using partial fractions. So we have f of t. This is the definition of the convolution. F of t convoluted. So this one is not multiplication. So f of t convoluted with g of t, this one, the definition is defined as the integral from 0 to t of f of t minus tau. This is multiplied by g of tau and then d tau. This is the definition of the convolution, right? So we can take the Laplace transform of the convolution that we proved in my first video, that is part 1 of the convolution theorem. So we proved that the Laplace transform of f of t convoluted with g of t. We proved this and the result was this. So the result is equal to capital F of s. This is normal multiplication by g of s. Right, so this is normal multiplication, but this is convolution. All right, so this is the Laplace transform of f of t multiplied by the Laplace transform of g of t. So we proved this in my previous video. So now what we are going to do in this question is to take the Laplace inverse of this function. So with this one, what we can do here is this one is going to be the Laplace inverse. If I want to take the Laplace inverse on both sides of this one is going to be the Laplace inverse of f of s multiplied by g of s, like this. And this one is equal to, this is going to return the convolution, which is f of t convoluted with g of t, like this. So for us to use the convolution theorem to find the Laplace inverse of a function, we will have to break the function down into the product of two different functions, just like what we have here. If we do that, then we can express them in terms of one function convoluted with another function, and then we can go ahead and use the definition of the convolution theorem, right? So the task here is to break this one down into two different functions, the product of two different functions, and then we can write them in terms of t convoluted with one another, and then we use the definition. So that is the first step. So now let's do that. We have the Laplace inverse of this function. This is s over s squared plus 1 all squared. I can write this one as 1 all over s squared plus 1, right? This is multiplied by normal multiplication. This is multiplied by s on top divided by the same denominator, s squared plus 1, like this. So we see that when we take the product of these two, that is going to yield our original function in the question, right? So this one, now we have two functions. So this one is now like f of s, and this one is now like g of s. That is from what we have here. So the convolution, this one is going to yield the convolution. Remember the Laplace inverse of f of g multiplied by g, f of s multiplied by g of s, that is going to return the convolution. So this one is going to be the Laplace inverse, right? The Laplace inverse of 1 all over s squared plus 1, right? This is convoluted with the Laplace inverse of s divided by s squared plus 1, like this. So that is the convolution. So this one is going to be, I'm not going to write this one all along. So the Laplace inverse of 1 over s squared plus 1 is what? That's the sine of t, because the Laplace transform of sine of t is 1 over s squared plus 1. So this is sine of t. This is now familiar, and this is now convoluted with the Laplace inverse of s over s squared plus 1, and this one is cosine of t. This is not multiplication. It simply means sine of t convoluted with g of t, or cosine of t. So f of t convoluted with g of t, or sine of t convoluted with cosine of t. So this one is the Laplace inverse of our function, which is s over s squared plus 1 all squared, like this. Now what is, we can't just leave our answer like this. If your professor wants you to leave your answer like this, then that is fine. But if you want to write it in terms of t, not in terms of a convolution, then we will have to use the convolution formula. So the convolution formula states that f of t convoluted with g of t is equal to the integral from 0 to t of f of t minus tau times g of tau d tau. Right. So now let's do that. So our problem now is to find this. So I'm not going to write this one all along, right? I'm just going to write the sine of t convoluted with the cosine of t, like this, because this convolution is the same as the Laplace inverse of this function. And this one, using the definition, that's going to be the integral from 0 to t of the first function. So the first function, but the variable is going to be replaced with t minus tau, right? So the first function here is sine of t. So this one is going to be sine of t minus tau, like this. And next one is going to be g of tau, right? So the g function is the cosine of t, but this one is now going to be cosine of tau. And then we are integrating with respect to tau, right? So let's integrate this one with respect to tau. So this question has now been turned into an integral question. So the sine of t, so when we find the sine of t convoluted with g of t with cosine of t, the answer should automatically be the Laplace inverse of the function that we are seeking to find in the question. Alright, so now let's do this. Now, using the double angle identity, so this one, using the double angle identity here, this one is going to be the integral from 0 to t. Now, using that is going to be sine of t, right? And then cosine of tau, right? Minus sine of tau, and then cosine of t, right? All this one is multiplied by cosine of tau. Cool. And then don't forget to bring the d tau. Remember, we are integrating with respect to tau, so everything t is a constant. So sine of t convoluted with cosine of t, this is equal to what? Now we can distribute in with the cosine of tau. So this one is going to be sine of t, and now cosine of tau times cosine of tau, that is going to be cosine square of tau, like this, minus next one is going to be cosine of t. Then we are going to have sine of tau and then cosine of tau, like this, all this one, and then d tau. Cool. Now let's split this one into two different integrals. Sine of t convoluted with cosine of t, this is equal to two different integrals, but we are integrating with respect to tau. This sine of t is a constant, it has nothing to do with tau, so I'm going to bring it out here as sine of t. Don't mind me about putting in the parentheses and ignoring them sometimes. So we have the integral from 0 to t of, this one is now left with cosine square of tau, right? But cosine square of tau from the double angle identity, just permit me to do it at one step, everything in one step. So cosine square of tau can be written as 1/2 into 1 plus cosine of 2 tau, like this. Cool. And then I'm going to bring the d tau, right? So this one is a constant which is here, and now cosine square of tau from the double angle identity can be written as this. Nothing special here. And now minus the next integral, which one is a constant here. So cosine of t is a constant here because it has nothing to do with tau. So cosine of t, like this. Then I'm going to have the integral from 0 to t of, this one is sine of tau cosine of tau, that is what is left inside the integral. And sine of tau cosine of tau, that one can be written as 1/2 into sine of 2 tau, like this. This is from the double angle identity as well. And then d tau. So these are the two different integrals. I'm just doing everything in one line. I hope it's clear. So now the sine of t convoluted with cosine of t, this is equal to now this 1/2 is a constant, so I'm going to bring it here, sine of t over 2. Now let's integrate. So we are integrating 1 in the tau world, this is tau, plus integrating cosine of 2 tau, that is going to be 1 over 2, and then sine of 2 tau. This is the integral, right? And then I'm going to put in the limits of integration like this. This is the first one. The second one, this half is a constant as well. This one is going to be cosine of t over 2 outside. And now integrating sine of 2t, that's going to be negative 1 over 2 cosine of 2t, because the integral of sine is negative cosine. This is tau. I'm sorry about that. All right, so you have to really be careful with the taus and the t's because they are confusing. Cool stuff. Now we have to plug in the limits. So the sine of t convoluted with the cosine of t, this is equal to, now we have to replace the taus with the t's. So this one is sine of t over 2, and then what is this? Replace tau with t. This is going to be t plus 1/2 sine of 2 tau. This one is now going to be 2t. This is the upper limit minus the lower limit. Lower limit, if you plug it here, this is 0. 0 for this one is 0, and sine of 0 is 0. So I'm not going to write that. We are done with this. This 1/2 here, if it comes out, is going to be positive, right? Negative 1/2 coming out, going to be positive cosine of t divided by 4, right? And then we are going to plug in the limits of integration. So the upper limit is going to be cosine of 2 times tau is now going to be cosine of 2t minus, if you plug in 0 there, cosine of 0 is 1, like this. So everything is now in terms of t. That is what we want. So sine of t convoluted with cosine of t, this is equal to, now we can multiply in, this one is going to be 1/2 times t times sine of t. That's the first one. Next one is going to be plus 1 over 4, right? Then we are going to have sine of t, and then sine of t and sine of 2t. Sine of 2t, right? And next one is going to be plus 1 over 4. We have the cosine of t, right? And then the cosine of 2t. And then the last one is going to be minus 1 over 4 times the cosine of t, like this. So what do we really have here with this one? So we can see that the sine of t, which is convoluted with the cosine of t, this is equal to, so I'm going to bring this one and this one together for now. So that is going to be 1/2 t times sine of t, and then this one, that is going to be minus 1 over 4 times the cosine of t. But these guys, I'm going to do something here. So 1 over 4 is common, right? So I'm going to write it like this, 1 over 4 outside. Then I'm going to write this, which is cosine of 2t multiplied by cosine of t, right? And I'm going to have plus sine of 2t, right? And then sine of t, like this. Cool stuff. Now using the double angular identity, let me do it here for you to see. So what is this? What is the, using the double angular identity, what is this one? 2t minus t, like this. This one, using the double angular identity, this one is going to be cosine of 2t, the first one. Then you have cosine of t, the second one. For double angular identity, for cosine, because you have negative here, this one is going to be plus. Then you're going to have sine of 2t, and then sine of t. Right, so we see that using a double angular identity, this one is just equal to this one here. They are exactly the same, right? Because they are the same, I can just replace it. So sine of t convoluted with cosine of t, this one is equal to 1/2 times t times sine of t minus 1 over 4 times cosine of t plus 1 over 4. Instead of this long guy here, what I'm going to replace it with this one. It's the same thing from the double angle identity. This is cosine of 2t minus t, like this. And cosine of 2t minus t is cosine of t. So this one is going to be 1/2 t sine of t minus 1 over 4 times cosine of t plus 1 over 4 times cosine of t, because this one is cosine of t. And we see that these guys will wipe each other out, and now what is left is the answer. So sine of t convoluted with the cosine of t, this is equal to this. So that means that the sine of t convoluted with the cosine of t, this is equal to 1/2 t times sine of t. Right, so the convolution of sine of t and cosine of t is 1/2 t times sine of t. So these ones separating them here are normal multiplication. So if you can recall, the Laplace inverse of what we are asked to find, which is s over s squared plus 1 all squared, is the convolution of sine of t and the cosine of t. And that is what we have. So we can just wrap up our video here, why not? So that means that the Laplace inverse of what we are asked to find, which is s all over s squared plus 1 all this one squared, like this. This one is going to be 1/2 t times sine of t, because this one is equal to the convolution of sine of t and then cosine of t. So you see that the convolution property is very nice. It allows you to calculate the Laplace inverse of some functions that will be impossible to calculate using the partial fraction decomposition. So that's the beautiful property of the convolution theorem. So if you really enjoyed this video, you give me a thumbs up, and then in part 3 of the convolution theorem, what I'm going to do, I'm going to solve another Laplace inverse of some complicated functions, which will be very difficult for us to integrate to calculate using the partial fractions. So if you enjoyed this video, give me a thumbs up, and then I will see you in my next video, where we'll continue to use the convolution theorem to calculate the Laplace inverse of some functions. I thank you so much for watching this video, and I'll catch you up in the next one. Bye bye.